We want to determine if the series summation from 1 to infinity 1 divided by n squared plus n converges or diverges. And if it converges, we want to see if we can find its sum. So let's rewrite the series in the following way. This is a summation from 1 to infinity 1 divided by n times n plus 1. So first let's expand the series. When n equals 1, we have from here, this is 1 divided by 1 times 2 plus 1 divided by 2 times 3 plus 1 divided by 3 times 4 plus 1 divided by 4 times 5 and so on. And this is 1/2 plus 1/6 plus 1/12 plus 1/20 and so on. So clearly this is not a geometric series. Geometric series has a common ratio between terms. So here 1/6 over 1/2 is 1/3, 1/12 over 1/6 is 1/2, and 1 over 20 divided by 1 over 12 is 3 over 5. So there is no common ratio. This is not a geometric series. Next thing we want to do is see if we can determine if this series diverges by using a test for divergence. Now, test for divergence says that we look at the limit as n goes to infinity of the sequence that determines the series. In this case, it says limit n goes to infinity of 1 over n squared plus n. If this limit is not 0, we can conclude the series diverges. But if the limit is 0, then the test for divergence is inconclusive. Well, clearly here the limit is 0, and we cannot conclude whether it converges or diverges from the test for divergence. Okay, so now what we're going to do is get back to the definition of what an infinite series is. So suppose we have a series from 1 to infinity of an. We're going to form a new sequence. We're going to call that sequence Sn. I'll use capital N for the index instead of the small n. This sequence is called the sequence of partial sums, and so Sn is defined as the sum of the first n terms of our series. So this is a1 plus a2 plus all the way up to an, and we can write it using sigma notation. This is a summation from small n equals 1 to big N of a sub n. Now, the definition of infinite series says that if the limit of the sequence of n partial sums exists, then the series converges to that limit. That is, the summation from 1 to infinity a sub n is defined to be the limit as capital N goes to infinity of Sn. So if this limit is finite, the series converges to that limit. If the limit doesn't exist, then we say the series diverges. The problem is, in most cases, it's very difficult to express Sn as a function of n, an easy function so that the limit can be evaluated. But in this case, we can do it because our sequence a sub small n is just a rational function. We can use partial fraction decomposition that we have already seen when we did integration techniques using partial fractions. So I'll rewrite the series in this way, 1 divided by n times n plus 1, and we can decompose it using partial fraction decomposition because the denominator is just the product of two distinct linear terms. So this is a divided by n plus b divided by n plus 1. Multiplying both sides by the denominator, we get 1 equals a times n plus 1 plus b times n. And just like when we did with the integrals, we can just plug in two values of n. First, we'll plug in 0 for n. That eliminates the b part, and that gives us 1 equals a. And now we plug in minus 1 for n. That eliminates the a part and says that 1 equals minus b, or b is equal to minus 1. So now our series can be expressed in the following way. First, we have the original form of the series, which was 1 divided by n squared plus n. We can also write it as summation from 1 to infinity 1 divided by n times n plus 1, and now further we can write it as summation from 1 to infinity a over n, which is 1 over n, minus, because b is negative 1, so this is 1 over n plus 1. So from here we can find a formula for Sn in terms of the last value, which is capital N. So let's look, for example, at S5. S5 is the sum of the first 5 terms of the series, and using this form of the series, it's very easy to simplify. So when n equals 1, we have 1 over 1 minus 1 over 2, plus 1 divided by 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, plus 1 over 4 minus 1 over 5, and finally when n equals 5, we get 1 over 5 minus 1 over 6. So look what happens. Minus half, plus half, minus a third, plus a third, minus fourth, plus a fourth, minus fifth, plus a fifth, and all we have left is the 1 and then minus 1 over 6. But notice here that our capital N is equal to 5, and this 1/6, instead of simplifying it, we can write it as 1 minus 1 divided by 5 plus 1. That is the last number in the partial sum, the last term, plus 1. So let's extend this or generalize this to a formula for Sn. Sn would then be 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1/4, and so on. And then when we have, let's say, n minus 2, this is 1 over n minus 2 minus 1 over n minus 1 plus 1 divided by n minus 1 minus 1 over n, and then the last term would be 1 over n minus 1 over n plus 1. So you see, same pattern. Halves cancel, a third cancel, a fourth will cancel with the next term, n minus 1 over n minus 2 will cancel with the previous term, minus 1 over n minus 1 plus 1 over n minus 1 minus 1 over n plus 1 over n. Everything cancel except this 1 and this minus 1 over n plus 1. So we have found a nice formula for the nth partial sum. It is equal to 1 minus 1 divided by n plus 1. And so now we can finish the problem. The series, we wanted to determine if the series converges or diverges, and the series was the summation from 1 to infinity. Let's write it in its original form, n squared plus n in the denominator. It is defined as the limit as capital N goes to infinity of Sn, the sequence of n partial sums, which we now have a formula for that. That's the limit as n goes to infinity of 1 minus 1 over n plus 1. Clearly this limit goes to 1 because this goes to 0, and so we have found that the series from 1 to infinity of 1 divided by n squared plus n, not only do we know that it converges, we know that it converges to 1. And that's the answer. This type of series, when we can find a formula for Sn by eliminating most of the terms because one is negative of the other, is called a telescoping series. So we'll do a few more examples of that. And so remember, telescoping series, a series where we can find Sn by eliminating the adjacent terms. For more videos, visit www.mathprepvideos.com.